macro model and how you can develop a simple macro model for an op-amp. We have already designed a two-stage op-amp, you have derived the specifications, and now how you can construct the macro model of the two-stage op-amp. We will give the overview. So first of all, what is the macro model? Macro model, it is actually constructed of some ideal components, that is resistor, capacitor, and some control sources, and few active components like diodes. Okay, what you have designed in your two-stage op-amp, all are actually in transistor level design, all are process specific. So your design is very much dependent upon what process you are using. In macro model, you will start from the specification of the circuit and you will derive a model that is based upon those RC, some control source and diode parameters that can be simulated any available SPICE simulator. So that is the utility of macro model. You can simulate the model anywhere in any available SPICE simulator, whereas you can't simulate the transistor level netlist, otherwise the process, you are not available with the process. Okay. So why macro model is done? First of all, suppose you have designed an op-amp of good specification. Now I want to use your op-amp and I want to fit it in my system. Now if I want to purchase it from you, but you can't make me available the actual transistor level design. So you can give me the macro model of the circuit of the op-amp, which is of the same specification. You will make me available that one. Now I will fit the model in my environment. I will simulate it and will test whether all my criteria is being satisfied or not. That is the intention to use the macro model. Actually, that's why, this is the reason it actually reduces the time gap between the release of the actual product, the actual chip, and that of the macro model. Okay, you are testing it before the actual chip is available. You are testing it, that is your all criteria is satisfied. Now you can purchase the chip. Okay, and in automated process design, if any tool is available, suppose you will just fix the rules, you will fix the specifications with which you will start. You will fit the specifications to the tool. It will automatically generate the macro model and you can test it. So there lies the objective of a tool which will develop a macro model. So there is a tool which will generate, which will start from specification of an op-amp and will develop the different circuit components, that different RC values and some control sources values of that particular macro model of that op-amp. So we will develop different libraries. Okay, what happens in actual design? In actual design, suppose there are a lot of transistor, you will just go on changing some transistor WIL value. Okay, so it may happen your gain is getting increased, but due to change of this WIL value, it may cause some other transistor which will go out of saturation, this kind of thing. Okay, so when you will go on starting this modeling, you will just divide the different specifications. You will divide it into different groups, different libraries. Each library should mimic different specifications. So at the end, you will just cascade all those things. So the entire model will get developed. So suppose for an op-amp, these are the stages which are going to model. So you have already, for that two-stage op-amp, you have already modeled, you have already designed the open loop gain, your dominant pole, gain bandwidth, then slew rate and common mode range, this kind of things. Okay, common mode rejection ratio, this kind of things we have derived from the specification. So before starting of the design, you just fix what are your requirements. Suppose your slew rate should be greater than 5 volt per microsecond, this kind of thing. Your bandwidth should be greater than some value. So after the design is complete, you just note the specifications. Suppose your slew rate is suppose 5.1 volt per microsecond, you got your UGB some 3.6 megahertz. you get. Now we start with the tool. You just put these different specification values to the model and different component values get evaluated. These are the different stages. Suppose at the input stage some bias current, that is get modeled here. Another thing is your input common mode range, that also get modeled. In frequency shaping stage, what it models your DC gain, dominant pole, and the capacitor. You see that capacitor compensation capacitor CC. It actually the your poles, your UGB, and your slew rate. The three things is being controlled by that particular capacitor. Okay, so your frequency shaping stage, it will model DC gain, dominant pole, slew rate, all these things. Again in the output stage, up to which point the output voltage can rise, or in the lower range. So this will, the intention of doing the output stage is to clip the output voltage, to fix it within certain limit. Okay, when you use ideal components and at the output stage you just use some clipping kind of circuit to fix the output voltage within certain range, as well as some temperature variation, TSRR, and common mode range, these kind of things. This is a simple frequency shaping stage of Opamp. Okay, now suppose a system has two poles. Okay, you can represent it by A by some voltage here, and this is V out. So what are the things here? What are the things you have to model? One is your open loop gain. You just consider one stage only. What is the thing to consider? Your open loop gain. Another thing is your pole. Okay. So what you get from here? Your open loop gain is G multiplied by R, DC gain. Okay. And this is equal to A. And what is the location of pole? P1 equals to 1 by twice by R into C. Okay. So suppose you have designed some analog circuit which has a gain of A. You know this one. You know this P1 also. Okay. So from A, suppose you guess some value of G. So from A, you will find R, and from R, P1 is also known. You can calculate the value of C also. Okay. So given any circuit, if you can simulate, you can calculate the value of, if you know the value of gain and pole, you can fix the value of R, C and G accordingly, so that it actually mimics the actual transistor level circuit. This is the objective of the tool. The objective of the tool is based upon some equations which is dependent upon few guess specification values and some unknown variables which are get solved. Okay, this is the objective of the Macromodel development tool. There is another stage. If you see in the second stage, this is actually what it models. It models another 0 also. Okay. If you solve this one, you will get some this type of function you will get. Depending upon your R2, R3 and previous stage R1, you can model this transfer function also. Your right hand pole, how you can model this one? What appeared in your Opamp actual design? Yeah, that's just using in this way. That will model your right hand pole. So there are different things. You are depending upon how many poles, how many zeros they are actually appearing in the actual design. You will just go on cascading these parts. Suppose there is it is a 3-pole system. You should add three GRC combination in series. Okay, for two pole, two combinations there. Okay, this will go on in this way depending upon your requirement. So another stage is your input differential stage. Suppose if you look from the input stage, from inverting and non-inverting terminal of the op amp, you will see that there is a high impedance between these two terminals. That is the differential mode impedance, and impedance from each terminal to ground. That is the common mode impedance. So you can approximately model it by using the resistors R2. R2 is the differential mode resistance, R1 and R3 are the common mode resistance. Okay. Similarly, this is the only the resistive effects. Similarly, if you add some capacitor parallel to R1 and R3 as well as R2, they will represent your capacitance value also, common mode capacitance and differential mode capacitance. Okay, as overall impedance you can input impedance you can model in this way. Okay, and you see this is the output voltage limiting stage. Suppose your transfer function is like that. So these are your clipping point. Okay, your ICMR up to within which range your op amp is operating in linear mode. Okay, so accordingly you will get this kind of response. Okay, so this is actually the output voltage limiting stage. There are different stages. Some common mode rejection ratio. This is also common mode rejection ratio. If you want to model this is also a combination of GRC. Okay. Similarly, how many response you want to get, you can just go on plugging each of the components, and as a whole, the circuit will model all the components of the circuit. Whichever is required, you just go on plugging those components on those libraries only. Okay, this is actually the basic approach. So finally, what we get. So your overall op amp, you can represent it in this way. This is your input stage modeling, input impedance modeling stage, and after that this differential voltage, this is actually differential to single ended conversion. This differential voltage, this will go to a frequency shaping stage and will get the appropriate frequency shape. After that, the output voltage is clipped within a certain range. Okay, so this is our approximate op amp macro model. So what it is applicable for all the op amp design. You have designed two-stage op amp, you can you can calculate the values for this one also. Also, if it is a big design, this same model it is applicable for that also. You need only the specifications. Okay, and the components and that particular characteristics you want to model, you just go on plugging in all those. Okay, that is the simple macro model, development of simple macro model. And what is its utility? You see, there is no active components in the device except in diodes. No transistor is there. So you can simulate it any available spice simulator. This is the main thing. This is the main thing you before why the spice modeling is so important. Okay. Okay, I will not go further. This is okay. One thing, just it has been seen that after simulating an actual transistor level netlist, where there are almost 50 to 60 transistors are there, almost 50 transistors are there for an op amp. It how many time it takes almost 1/6 simulation time, 1/6 improvement, sorry, 6 times improvement in simulation time for the macro model simulation. Okay, so that is a major improvement. And this model is developed, one model has been developed in BSIM3 also, so you can simulate it everywhere. And accuracy margin, it has been also found that it is almost 10%, maximum 10% deviation from the actual transistor level simulation. That is also pretty good. Okay, that's all.